Okay guys, so today we're talking about angle relationships within polygons, and so the first thing we need to discuss is what exactly makes a shape a polygon. So a simple polygon should have sides that are made up of segments. So obviously if all of the sides of a figure have to be made of segments, then those sides are always straight and should never curve. So anything that has a curved edge is not considered a polygon, okay? Those segments also connect at vertices at the corner. So we should have edges and vertices, and obviously a vertex can only connect up to two sides, okay? Now, segments that connect opposite vertices, so vertices that are not in consecutive order, that would be what we consider a diagonal. So anything that kind of cuts across the shape, connecting two vertices that don't come in consecutive order would be a diagonal. And if we extend one side of our polygon, then we get an exterior angle created on the outside, kind of like we discussed the other day. And then you would have, for instance, if this is your polygon and you extended that side, now you've got an exterior angle that's adjacent to the angle right next to it on the inside. Okay, so examples of things that are polygons. You have your basic shapes like your squares, triangles, hexagons, pentagons, etc. Your star shapes. I mean, they can look as weird as you could possibly imagine as long as all of the sides are straight and no curves. So examples of things that would not be polygons would be circles, shapes that have curves in them, or shapes that don't close. So for instance, if that was our figure, if there's a gap here and the vertices don't actually connect, then obviously that's also not considered a polygon. Okay? We can classify polygons based on their shape by calling them convex versus concave. Convex, technically the definition is that I should be able to join any 2 points between the shape and have the segment completely contained inside. The easiest way to remember this is that convex shapes have no dents. So what we mean by a dent would be a place where the shape kind of bends in on itself. So if we don't want that, then we think of these figures as kind of your nice, whole, round, neat, solid shapes, okay? Concave, on the other hand, if we kind of think of the second part of that word, caving in on themselves, these figures do have dents. So these would be things like your star shapes, or maybe, you've got a shape that kind of looks like a crown. Any place where the figure caves in on itself, if it dents in, then that would be considered concave. If we have no dents, then that would be convex. Okay? Hopefully we remember, because we've used this term quite a lot now, that equilateral just means all our sides are congruent. And we see that marked on a picture by the tick marks. All right? Equiangular similarly means that all of the angles are congruent. And we would also see that marked on a picture by looking for the angle markings. And remember, we learned the other day that if a shape is equilateral, that automatically implies that it is also equiangular. So the term regular combines both of those. So if we say a polygon is regular, that means it is both equilateral and equiangular. And hopefully we kind of remember that term from Unit 2 when we talked about building the regular hexagon. So all sides should be the same. All angles should also be the same. Okay? All right, so let's talk a little bit more about the diagonal. So remember, if we have a segment that connects non-consecutive vertices, we call that segment a diagonal. So by non-consecutive, we just mean not in order. So they don't necessarily have to be across from each other, because if we have an odd number of sides, our vertices aren't across from each other anyway. But they just have to be not in order as if you were drawing the shape. So for instance, if we look at this rectangle, if we were to number those vertices, 1 and 2 would be considered consecutive because 1 comes right before 2. However, 1 and 3 would be non-consecutive, so that would be a diagonal. 2 and 4 would also be non-consecutive, so that would also be a diagonal. Okay? Let's skip over to the pentagon at the end. All right, if we name the vertices, sometimes that just helps to kind of keep up with the diagonals. We obviously can't connect 1 and 2, but we could connect 1 and 3. We could do 1 and 4. Can't do 1 and 5. We could do 2 and 5, 2 and 4. We could do 3 and 5. We've already done 3 and 1. And now at this point, we've connected all the possible options. Okay, so notice if you were going to count the total, we have 1, 2, 3, 4, 5 total diagonals for a shape that has 5 sides. Okay, so you take a second, kind of on your own, go through and figure out the diagonals for the shapes in the middle, for that 4-sided figure and the 6-sided figure. All right, so now when we talk about polygons being regular versus not, remember regular means all the sides are the same, all the angles are the same. So you should see on your paper you've already got markings. Mine aren't showing up on the screen. But for you, if we see the markings and the markings, then we would say yes, that figure is a regular equilateral triangle. All right, similarly for the pentagon secondly, again, if we see all of those markings, yes, that figure is regular. Now for your third shape, that trapezoid, hopefully we can easily recognize that that would be a case of non-regular, because even though these two legs are the same, the bottom and the top are clearly not equal, and hopefully we also recognize that all 4 of those angles are not the same, so that would also be no. All right, if we're assuming this is a square, then that would be yes, the only regular 4-sided figure. And then again, down here for this 8-sided figure, for that octagon, if we see all equal sides and all equal angles, that would also be yes. Okay? All right, so now let's get into the good stuff, talking about the angles. All right, so for each of these shapes below, we want to cut the polygon into as few triangles as necessary to fill the shape. So for instance, when we look at figure number 1, figure number 1 is already a triangle, so we don't need to cut it anymore to turn it into a triangle because it already is one, okay? So now, number of sides, a triangle has 3. Number of triangles we made, it's already a triangle, so that is one whole triangle, okay? And then hopefully we remember from last Thursday, the sum inside a triangle is 180 degrees if we added all 3 angles together. Okay. All right, for that second figure, that would be a quadrilateral, a 4-sided shape. All right, now you could cut this one of 2 ways. We could kind of cut across the diagonal from the bottom left to the top right. You could also come in the other direction and cut from the top right to the bottom left. But regardless of how you do it, notice when we cut here, now we've made a total of 2 triangles, and we do not need to cut any more. Okay? So number of sides, 4. Number of triangles, 2. Now, if one triangle has a sum of 180 degrees, then if this shape has 2 triangles, then it stands to reason that its sum would just be 2 times 180, which is a total of 360 degrees on the inside. Okay? All right, figure number 3, that's a 5-sided figure, which would be a pentagon. Number of sides we see, 5. Again, you could cut this lots of different ways, but let's say I cut here. That's one triangle. And then in the space I have left, let's say I cut here. That makes 2, 3. So now we could obviously keep cutting, but remember we want to cut it into as few triangles as needed. So in this case, that's 3 total triangles. So if one triangle has 180 degrees and this shape has 3, then in this case, that total is 540 degrees. Okay? You take a second, do this last shape. So we've got a 6-sided figure, that's a hexagon. So we see 6 sides. How many triangles could we make? What would be the sum of the angles on the inside? All right, so hopefully we've recognized kind of by the pattern, if you look at your chart, for any given figure, all right, if you were to compare the number of sides to the number of triangles, so like 3 to 1, 4 to 2, 5 to 3, and hopefully we got 6 to 4, then in this case, hopefully we notice that the pattern is that the number of triangles you make should always be the number of sides minus 2. So whatever number of sides we have, we should be able to make 2 less triangles than that. So if we had a 10-sided figure, we should be able to make 8 triangles. A 20-sided figure, we should be able to make 18 triangles, okay? And then hopefully we've recognized that between column 3 and column 4, all we're doing is we're taking the number of sides and we're the number of triangles, and we're multiplying it by 180. So if n minus 2 represents the number of triangles that we made, then we would multiply that by 180 to get the sum of all the angles on the inside. And that works for any polygon, regardless of the number of sides and regardless of whether it's regular or not, okay? Now, that gives us the sum. That's the total of all of the angles on the inside. So what if instead we only want 1? If I just want a single interior angle on the inside, in that case, I would need to take the total that you just found, and I would need to divide that by how many angles we see or how many sides we see. They should be the exact same number. But now keep in mind, that would only work if the shape was regular. So for instance, back up at the top, we could not take 540 and divide it by 5 and figure out how big each of these angles is. Because in that case, all the angles are not congruent to each other. But if we had a regular shape and all the angles are supposed to be congruent, then we can divide that total evenly and find a single interior angle on the inside, okay? All right, so let's kind of go through and just do that again for each of our kind of major, hopefully well-known polygons. So for instance, polygon number 1, triangle. All right, we have 3 sides. We saw up top that its interior angle sum is 180 degrees. So if I took 180 and divided it by 3, then each of the angles on the inside should be 60, okay? All right, now, hopefully again we recognize from day 1 that these 2 angles are supplementary. We have a linear pair if we just extend one of those sides to get the exterior. So if the inside is 60, my exterior would be 120, because together that should make 180 degrees. All right, for a 4-sided figure, quadrilateral, 4 sides. We saw up top that if I did 2 times 180, that would be 360. If we did 360 divided by 4, then each of the angles on the inside would be 90. And then each of the angles on the outside would also be 90 degrees. 180 minus 90 is 90. All right, for your pentagon, our 5-sided figure, we saw up top that if we did 5 minus 2, that's 3. Times 180 gives me a sum of 540 on the inside. And if I take 540 and divide it by 5, then each angle on the inside is 108 degrees. And then the adjacent angle next to that on the outside would have to be 72. All right, six-sided figure, those are your hexagons. Interior sum would be 6 minus 2 times 180, 720 degrees. 720 divided by 6 gives me 120 degrees on the inside and 60 on the outside. So notice how that's very similar to, but kind of like the opposite position.